Okay, so hello everyone, good evening. Hope you are doing well. So today this is the second part of thermodynamics video, and today we are gonna continue with the topic quasi-static processes and Reynolds number and about some degree of freedom and Poisson's ratio. So let's get started and welcome to our channel named Phi Math. So first of all, what is Poisson's ratio? So Poisson's ratio is denoted by gamma, written like this or like this in computer language. This gamma is equal to Cp over Cv. Okay, I've already told you in part 1 what is Cp and what is Cv. So let me remind it once again. The Cp is the molar specific heat at constant pressure, while the Cv is the molar specific heat at constant volume. So the gamma or the Poisson's ratio is just the ratio of that, and because it is a ratio, this is of no unit. So this is a unitless constant for different types of gases. So as you can see, here is a table for monoatomic gases, diatomic gases and polyatomic gases. So the monoatomic gases include gases like neon, helium, etc. Okay, so these type of gases have 3 degree of freedom. So what do we mean by degree of freedom here? So the degree of freedom is something let's say a ball. So a ball can move in x, y, and z, three directions, or x, y, z plane. Okay, and this ball can also rotate, or with respect to x-axis, y-axis, and z-axis. But as we already said, this is a ball, and a monoatomic gases are gases with only one atom. So they are just a little bit like spheres. So they look exactly alike when they are rotated. So it doesn't mean anything to rotate them. So only three things can be possible. Either they can move with respect on the x-axis, y-axis, or z-axis, or a combination of that. So their degree of freedom is 3. Okay, maximum degree of freedom could be 6 because 3 translatory motion and 3 rotational motion. Okay, so gamma or the Poisson's ratio for this would be Cp over Cv, and it can also be written as F plus 2 divided by F, where degree of freedom is represented by F. So as we can see, 3 plus 2 is equal to 5 divided by 3, or simply 1.66. Okay, if we look at diatomic gases, these gases include O2, N2, H2, which just form one bond to complete their octet, and then after that they are stable. So if we look at oxygen or any of these gases structure, they are little bit like this. So as you can see, this structure can move in x, y, z, three different direction, and can rotate about three different direction. So they can either move so in either direction, so their degree of freedom will be 3 in the translatory, plus see they can rotate about this axis, which would just make a difference. Okay, they can just rotate about this axis, which would also make a difference. But if they rotate about this axis, then that will not make any difference because that will just be the same shape again. So it would be 3 plus 2 to rotation, that is equal to 5. So applying the gamma or Poisson's ratio formula, we get f plus 2, which is 5 plus 2, that is equal to 7 divided by 5. Okay, so now after this we have polyatomic or non-linear gases. Okay, so these gases are little bit okay, so we left linear. So polyatomic linear gases are like CO2. Okay, it is denoted by this structure. So as you can see, they are consisting up of more than two atoms. So the linear atoms are just same treated like this thing. So they also have degree of freedom to be 5, and their gamma is also is equal to 7 by 5, which is 1.4. So if we look at polyatomic non-linear molecules of gas, we get example like NH3. So the structure of NH3 is like, okay, let us take CH4 too. So it is like N with three bonds with hydrogen. So as you can see, they can either translate in three different directions. So they will have three translating motion degree of freedom. Also, they will have three different rotational degree of freedom, because if they rotate about any of the axes, that will make a difference. So they get a maximum number of degree of freedom, that is equal to 6. Okay, so as we can see, 6 plus 2 is 8 divided by 6, cancelling this out, 4 over 3 or 1.33. Okay, moving on to law of equipartition of energy. Okay, so this says that each molecule has half kilojoule energy in each degree of freedom. Okay, so now here we know that ideal gas have only kinetic energy and no potential energy. Okay, so one molecule having 1 degree of freedom would have U is equal to half kilojoule. We know this. Now multiplying with F on both sides, we will have having F degree of freedom and U is equal to F by 2 kilojoule. Okay, so uh, sorry, this is KT temperature. Okay, so here K is the Boltzmann constant. Okay, and its value is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, so now we know for one molecule. Now let us multiply it by n. Okay, so for 1 mole molecules, we are gonna multiply it with uh, Avogadro numbers, Na, Ket. So here, as we can see, Na, Kt is R or Reynolds number. Okay, so now what we do, we just take for n molecules. So now for n molecules, it would be F by 2 nRT. Okay, here we can say delta U is equal to F by 2 and R delta T, like I told you in previous class, to differentiate each side. Okay, so for ideal gas monoatomic, this would be, for ideal gas I have told you the degree of freedom for monoatomic ideal gas is 3. So for ideal gas which is monoatomic, U would be equal to 3 by 2 nRT. Okay, so after this we have a question. Okay, quasi-static process, and after that we have a question. So let us first answer the question because it is much more related to this topic. Okay, so the question is, prove that water has specific heat of 9 R, where R is the Reynolds number, assuming that when water expands, its volume changes negligibly. Okay, so because we know that any ideal gas is kinetic energy only, so water has both kinetic energy and potential energy because it three different forms and three different types of atom. So if we take a look at kinetic energy only, then one atom would mean 1 degree of freedom. Okay, that would be equal to 1 by 2 kT from the previous formula, where the value of F is taken to be 1. So for 3 atoms, just multiplying it by 3, you will have 1 degree of freedom. That would be equal to 3 by 2 kT. So from here, n moles water would mean 3 times F by 2 times nRT. That is equal to 9 by 2 nRT. Okay. So here this F value is also equal to 3. Okay. Because it has 3 different translatory motion. Okay. So potential energy, which is equal to U, is 9 by 2 nRT. Okay. From the previous formula. And the total energy would be 9 nRT. Okay. So we know that delta Q is equal to NC delta T. From here we can say C is equal to delta Q divided by delta Tn. So we are doing this because we need to prove about specific heat and not about total energy or kinetic or potential energy. Okay, so from here we can say delta Q is equal to U plus delta Q is equal to U plus integration PD. Here this is 0 because change in volume is 0 negligibly, which means the delta V is equal to 0. Okay, so let us erase that for space because we have talked about it. So from here we can see C is equal to, see from here we get delta Q is equal to U. So from here we can easily say that C is equal to delta U, or U simply, divided by N delta T. Okay, why did I make it a capital N? Okay, so now we get delta U is equal to yes, this we have written, just removing delta for less confusion for you. So we can say it as 9 by 2 N R delta T divided by N delta T, and actually this is 9 because total energy is 9 and R T or delta T. Okay, so from here delta T gets cancelled and N gets cancelled, so we will be left with 9R, which is our result and which is what we just wanted to prove. Here the Reynolds number is 8.314 joule per mole Kelvin. See, in chemistry we get 3 or more different values for Reynolds number for different units, but in physics we just follow one unit, which means that we just need. So if we just take a look at the table once again, so from here we can see that for monoatomic gases the value of degree of freedom is 3. Okay, so from here, did you remember that here we have taken it 3 by 2? Okay, so as we can see it is 4 by 3 and we have taken 3 by 2 in this question. That is because in this question we just have taken water to be as monoatomic. Okay, so now moving back to quasi-static process. So quasi-static process is a theoretical process. It cannot happen in reality. In this process what we do, this is process which is carried very slowly such that the system or the thing is in gas is in equilibrium and we do not get any loss of energy. So that means there are some things that cannot happen in reality, like this thing would should be frictionless. That cannot happen in reality. Also, like we take this example. So for this example, we have to remove the sands one particle at a time so that the pressure or the weight of these sand molecules will not change much, and the gas will not be able to expand much, but just a little bit change in mass, and soon the lid will move or the piston will move slowly up. Okay, so this is different from reversible process because some permanent energy loss can be there. Okay, so now we can simply say it in the language of physics as we have to make equilibrium after each step. So in this case, the step is removing a grain of sand. So after a grain of sand is removed, the piston will slightly raise up, and what we will have a new equilibrium state. After this, we have the concept of heat engines. So heat engines, they are different type of engines that we face in day-to-day life, like diesel engine, petrol engine. But heat engines are the engines that take heat from a source and utilize some part of it as work, then release the remaining heat into sink. So I hope you remember the title page image which had been in the first page or the first slide. So here, as we can see, this thing is also a heat engine. Okay, so how is this a heat engine? What we do is, for this thing, we take our palm, okay, and place this engine on our palm. And what this does is that it takes heat from our palm and change it into work by rotating itself. So this is caused, as we can see, there are two different plates here. So the hand will heat up this plate, and this plate is cold. So as you know that heat will travel from hot place to colder place. So the heat will travel into this cold place, and after we remove our palm, this place would be cold, but this place is hot. So utilizing this hot and cold simple concepts, this can rotate even very fast because the temperature difference would be very much. Though this is just on a small scale, and on large scale it is very difficult. So for now, we are gonna study about Carnot engine, which is the engine, or there was a person named Carnot who proved that his engine is the best, and no engine, even theoretical or practical, could have more efficiency than his engine. Okay, so this Carnot engine is not that easily practically possible, but still his engine is a theoretical with most efficiency, and the efficiency is not equal to 100%. That we will answer this question after we derive. Okay, so now from energy conservation we know that q1 is equal to w plus q2. Okay, for this figure, like this is a source with temperature. This is the most basic heat engine. So we provide a Q1 which is cost for us, and this thing does work on piston or anything. Okay, after that what we have a working fluid. Okay, so this thing just gives us output or work for our, so work, and also this temperature or the waste is then thrown into a sink with temperature TL. So efficiency, also denoted by eta, is just output divided by input, or output in this case is work done divided by input, which is Q1 or cost. So work done, what is work done? Change in heat, Q2 minus Q1 divided by Q1. As you can see, work done is Q2 minus Q1. Okay, plus I think I did a mistake. Okay, sorry. So this is a mistake. Okay, so now we can say eta, just dividing Q1 in both of them, is 1 minus Q2 over Q1. Okay, okay. So this is our formula for efficiency and Carnot engine. Okay, so all engines in real world just try to behave like Carnot engine. Okay, so Carnot engine, as you can see, we have provided work. Heat is given out to Ti. Thanks, I did a wrong image. Whatever. So as we can see, this thing is opposite. Okay, so what we actually have, this is for heat pumps and refrigerators. Okay, so for Carnot engine, we have this type of diagram. So as we can see, the temperature high is given to piston. In this case, this thing is piston, which does work for us to temperature C, or we say temperature low. Okay, so now this comprises of four main steps. Okay, the first is reversible isothermal expansion. As we can see, the volume is expanding, so expansion. Then there is adiabatic expansion, reversible, all things are reversible. Okay, then we have isothermal compression, TC. Okay, then we have adiabatic compression. So all of these I have told you in previous lecture are thermodynamic states. So P1 V1 T1, P2 V2 T1, because temperature is same in isothermal. Adiabatic, so that will just change. So P3 V3 T3, because if I take T2, then you would get just a little bit confused. So P4 V4 T3, or let us just take T2 for simplicity, because we skipped T2 for you. So as we can see from here, the total work done would be the area under the graph. So work done would be W1 plus W2 plus W3 plus W4. All of the processes work. This is getting a little bit long. So nRT1 ln V2 by V1, I just derived them in previous lecture. All of these works, plus nRT2 minus T1 divided by 1 minus gamma, plus nRT2 ln V4 by V3 plus nRT1 minus T2 divided by 1 minus gamma. Okay, so from here we can see that this thing and this thing gets cancelled. If we take minus common from here, then we will get same expression, but with this would be a minus sign, so these two things will get cancelled and we will just be left with this small thing. Okay, so I'm erasing that. So now this is just a sum of two things. So we know that in isothermal process delta V is equal to 0, change in volume for isothermal, delta T is equal to 0 too, and then we will have delta Q is equal to 0. Okay, okay, so sorry, delta Q is equal to delta W, change in work done. So from here what we can see, we can say that delta Q is equal to N R T1 ln V2 by V1. How can we say this? We can say this because this is delta V plus delta W. Delta Q is equal to delta W. This is just derived from here. So delta V is equal to 0 as we just said. That means this thing gets cancelled out and we will get delta Q is equal to delta W only. Okay. So from here we know, like in the heat engine, efficiency is W by Q1. Okay, so that would be equal to NR T4, this whole thing divided by Q1, T1 ln V2 by V1. As we can see, most of the things will get cancelled. So as we can see, ln V4 by V3, NR get cancelled, and we can see that we will be left with T2 over T1 ln V4 over V3. We have divided that thing too, so we will get a 1 extra. See, this ln V2 by V1, not V3, V2 by V1 is also divided here, as we can see. So from here, we can just say it, just using the property of logs, we will get 1 minus T2 by T1 ln V3 by V4 and ln V3 by V2 by V1. Okay, we have just applied the property of log. Okay, just flip these things. Why? Because I'll just tell you a little bit later. Also we know that T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. So from here, in two adiabatic processes we are applying this in process 2 to 4 and process 4 to 1. So I'm just applying it in process 2 to 3. So T1 V2 to the power gamma minus 1 is equal to T2 V3 to the power gamma minus 1. Also we know T1 V1 to the power gamma minus 1 is equal to T2 V4 to the power gamma minus 1. So dividing these two things, we will just get V2 over V1 is equal to V3 over V4, because the power will also get cancelled. Okay, so as we can see, these things are equal. So we will just get simplified 1 minus T2 over T1. Here, this thing would also be equal to uh, uh, 1 minus Q2 over Q1, like we derived in the engine's case, and that would be applicable in each and every engine. So from here we get these two things, or we will get this amazing ratio Q2 over Q1 is equal to T2 over T1, which is amazing. So just remember this thing for Carnot engine and this thing for Carnot engine. Everything except this is not that useful, while the derivation is a little bit long. So now the question is, like I said, this ln v2 over v1 or ln v2 over v1 get cancelled. Now the question is, why cannot be the efficiency be 1 for Carnot engine? So like we just derived for the Carnot engine, efficiency, which is denoted by eta, is equal to 1 minus t2 over t1. And for this to be 1, so if this is equal to 1, let me write it here, is equal to 1, then what does this mean? This just means t2 over t1 is equal to 0, which means that t2 is equal to 0, Kelvin, not degrees. And practically t2 cannot be 0 Kelvin, so it is very hard to get full efficiency. Okay, so after this we have heat pumps and refrigerators, which are just the opposite of Carnot engine. So these refrigerator or ACs are just doing this thing, just doing the opposite. Wait a minute. Okay, as we can clearly see. And now the coefficient of performance. Here we defined coefficient of performance, that is equal to benefit divided by cost, where benefit is the output or the work divided by the heat divided by work, which is denoted by alpha q2 over w. Okay, so what is the heat pump is basically a refrigerator, but it has been changed. So we now want hot air or heat. In refrigerator we just want the remove heat, but in heat pump it is just like a refrigerator with the back side on, or the AC with back side on. So beta would be same q1 over w. Okay, so now the only difference is that we just provided the work just same, but now in the case of refrigerator we want this TL, and in the case of the heat pump we want this TH. Okay, so we need to prove beta is equal to alpha plus 1. So it is a very easy proof. So alpha is equal to q2 over w, and beta is equal to q1 over w, or w plus q2, as we have done work to get w1 or w. So from here, just cancelling this out, we will get beta is equal to 1 plus q2 over w. And this thing, we just know this thing. This is just the alpha. So from here, we have thus proved beta is equal to alpha plus 1. A very simple proof. Okay, so after this, we have just reached to the end of today's class. And the last thing that I want to discuss is this isothermal and adiabatic graph difference, because there is one question, which is why is this adiabatic process much more steeper, has much more steeper graph than this isothermal. Okay, to answer this question we are gonna look at both of the processes. So first let us take a look at isothermal, and then let us look at adiabatic. So now looking at both of these processes, green for isothermal. In this process, PV is equal to constant, as we all know. So from here, differentiating this thing, we get P dV or P delta V plus delta PV. We don't know that pressure is constant, is equal to 0. From here, we can see P delta V is equal to minus V delta P. or the opposite is also true. Okay, so from here just dividing, we get delta P over delta V is equal to minus P over V. Okay, so delta P over delta V is just the slope, so this is just minus P over V for the isothermal. Now let us look with light blue color about adiabatic. So in adiabatic what we have PV to the power gamma is equal to constant. So differentiating this thing as we have done in isothermal, same thing doing again, we get P gamma V to the power gamma minus 1 plus V to the power gamma delta P is equal to 0. Just applying the product rule for differentiation. From here we can say that delta P array delta P over delta V is equal to minus gamma PV to the power gamma minus 1 divided by V to the power gamma, or just simplifying it even more, we get PV over delta P over delta V adiabatic is equal to minus gamma P over V. So as we can see from both of these equations, comparing, you can say, type of, we have got this and we have got this. So we can see minus P over V is common in both of these. So we can say slope, let us denote slope by M. M of isothermal is equal to minus gamma times M of adiabatic. So as you can see, this is just a multiple of gamma and it would be positive. So as we can see, slope of adiabatic is much more than the slope of isothermal. Okay, so after this we just have the second law of thermodynamics and different statements about it. Okay, the basis. Okay, so I don't have the slide for this. So for the second law of thermodynamics, we have different statements about it. So it sets practical limits to the direction of some physical processes, like a bursting of tire. So as we can see, if a tire is burst, okay, it is a bursted tire, the air has escaped. So can it even happen in reality that this busted tire would just change into this back, which is not possible? So the second law of thermodynamics just says that. It also explains why efficiency can never be one, but there is no proof for this law. But the main thing is that this law has never been disproved. It always occurs in every situation. No situation has occurred in which this bursting of tire can be just remade. If you just change the temperature or the pressure, different things, also then you cannot get the perfect tire back. Okay, so there are two different forms of this law. The first is Kelvin Planck statement. Okay, and the second is the Clausius statement. These two people just provided different statements. So if you look at Kelvin Planck's statement, they says that no process is possible whose only result is absorption of heat and then its complete conversion into work. It says that Q2 can never be zero. It implies that eta is equal to 1 minus Q2 over Q1, and it says that Q2 can never be equal to 1, which means n is never equal to 1. N is not equal to 1, which means just Q2 cannot be equal to 0. Okay, this is just saying, okay, and the Clausius statement says that no process is possible whose only result is transfer of heat from a colder object to hotter object, as we never see this thing in reality. Like if we have put it a ice cube and the metal bar, hot metal bar, then we will see that the ice will melt. But it will never occur that the metal rod will get even hotter and the ice will get even colder. Okay, so that means that transfer of heat can never happen from a colder object to a hotter object. So there should be any external help which is required for that. So if we just take a look at a difference between reversible and irreversible process, the last topic for this video, we get a reversible process is a process in which the participants go back to their initial form by include inclusion minor or negligible change in their surroundings, like melting of ice. If ice is melted into water, we can just transfer it back into ice. But if we just tear a paper, let's say, okay, then we can never get it back. Okay, so this thing is not possible. So irreversible process is a naturally occurring phenomena in which the participant do not go back to their original position. Okay, so as we have just completed this video, thanks for watching and see you soon in the next video. The next video is probably gonna be of thermal properties of matter. Till the time, stay tuned and see you soon. Thanks and bye bye.